10.6 power series. This is the last in our sequences in series. So if you have a sum of an infinite geometric series, such as 1 plus r squared plus blah, 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 all the way to whatever the last term is, and it equals 1. The sum of your infinite geometric series is 1. With a common ratio, it converges to the sum of a sub 1 over 1 minus r. So we found when we did geometric series, we know that if it's infinite, the sum is a sub 1 over 1 minus r. And if your r is, absolute value of r is less than 1, then your sum from 0 to infinity of x sub n plus 1 plus x squared plus x cubed. So every time you multiply by x, it's 1 over 1 minus x. That's because the first term is 1. Okay? In general, we call this a power series. So a power series basically is anything of the form... Oh, wait a minute. Hold on. Let me fix this. I have too many x sub n's in here. Okay. So now let's look at this again. Okay. So anything that's of the form, even if you've got a coefficient in front, that's in the form of a sub n, x sub n. As you go through, this is basically called a power series. So remember, a power series is the form x sub n or a sub n, x sub n. The sum is going to be a sub 1 over 1 minus r, or in this case, 1 over 1 minus x for this one. It depends on the problem. So I want to use the sum from n to infinity of a sub n over x sub n to find a power series representation of g of x equals 1 over 3 minus x. Which means I basically want to turn what is a rational function into a power series representation. So the first thing you're going to do is you're going to set that g sub x equal to what we just call f sub u. We're just going to call it a different equation. So my 1 over 3 minus x, we know if it's a power series, it equals 1 over, instead of there being an f of x, instead of it being 1 over 1 minus x like it was on the last screen, we're going to make it 1 minus u. So if I solve for u, that basically is this times this. So we have 3 minus x equals 1 minus u. So subtract 1. That gives us 2 minus x equals negative u. So u equals negative 2 plus x. So u equals x minus 2. So as a power series, you're going from n equals 0 to infinity. And the function is x minus 2 to the n. So all you're doing basically here is converting what is just a rational function, and you represent it as a power series. So indicate on which the interval converges. So remember, if you are going to infinity, more than likely it's going to converge, especially if it's between negative 1 and 1. So to find where it converges, you're taking this here, which is your x minus 2, and it has to be less than 1. Because remember, we said whatever your r is has to be less than 1. Which means that your x minus 2 has to be less than 1, and your x minus 2 has to be greater than negative 1. So we have to sandwich it between negative 1 and 1, because that could be a negative 1 or that could be a positive 1. So what this means, or expanded out, is negative 1 is less than x minus 2 is less than 1. So if I add 2, that gives me 1 less than x less than 3. So basically it converges on 1 to 3. So if you were to plot 1 over 3, 1 divided by 3 minus x, it converges between 1 and 3, basically. Last part is we also want to find an expression for the sixth partial sum. So if you remember, let me move this up higher. Okay. So if we want to find sixth partial sum, if we're starting with 0, so 0, 1, 2, 3, 4, 5, 6, 7. So 6 numbers is 1, 2, 3, 4, 5, 6. So we stop at 5, and that's x minus 2 to the n. So when I want an expression for the sixth partial sum, I just want you to write it out. So if I plug in x minus 2 to the 0 plus x minus 2 to the first plus x minus 2 squared plus x minus, x minus 2 cubed plus x minus 2 to the fourth plus x minus 2 to the fifth. Well, x minus 2 to the first is 1. So then it's plus x plus 2. Not plus, minus. Plus x minus 2 squared plus x minus 2 cubed plus x minus 2 to the fourth plus x minus 2 to the fifth. So this is what a sixth partial sum, an expression for a sixth partial sum would look like. Okay, exponential series, anything e to the x, you can also write as a partial sum. So we have e to the x is going to be equal to the sum of n equals 0 to infinity, x sub n over n factorial equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. So where the e to the x come from is basically this series multiplied out. So I want to use the fifth partial sum to find an approximate value of e to the 1.5. So my e to the 1.5 is equal to the sum of n equals 0 to infinity of 1.5 to the n over n factorial. So this is mathematically how you're going to find the value of e to the 1.5. So you'll plug it in. So you've got 1 plus 1.5 plus 1.5 squared over 2 factorial plus 1.5 cubed over 3 factorial plus 1.5 to the fourth over 4 factorial. So if I want fifth partial sum, I basically just want you to do 5 of them. After a while, the number will be so small that it won't have an impact on it. So when I add all those together, you're going to get 4.398. So that's where the e values come from. It actually is just a series of numbers added up together. Power series can also be used to represent sine and cosine. So where your sine values come from is also can be written as a pattern. So for cosine, it's negative 1 to the n power, x to the 2n power, over 2n factorial. And so when we plug in n equals 0, we're going to get 1 on the bottom. When we plug in 1, we'll get 2, 2 will get 4, 3 will get 6. That's why these basically go by even numbers. So whatever these even numbers are, the exponents are the same, and they alternate signs. And it starts with a 1, so it starts plus, minus, etc. And so we're basically just going to plug it in. I want to use the fifth partial sum to approximate the value of cosine of pi over 7. So my cosine of pi over 7 is going to be equal to 1 plus, okay, so then we're putting in pi over 7 squared over 2 factorial plus pi over 7 to the fourth over 4 factorial plus pi over 7 to the sixth over 6 factorial. So that's 1, 2, 3, 4. I need one more. Oops. Wait a minute. I gotta fix my signs. This is a minus. This is a minus. Minus, minus. And then plus pi over 7 to the 8th over 8 factorial. And so when you do all of this and you multiply it all out and simplify it all out, you get about 0.901. So sine is kind of the same way. It's got its own pattern. So you have negative 1 to the n over x to the 2n plus 1, 2 plus 1 factorial. And so for the sine of x, it starts with x. And then your denominators are now like the odd numbers, like 3, 5, 7. Same thing on top. And then again, it starts positive, negative, positive, negative. So I want to use the fifth partial sum to find a power series that approximates pi over 5. So I'm just going to plug it in. So my, let's use a different color. So my sine of pi over 5, so my pi over 5 is my x, is going to go into all of these. So I have pi over 5 minus pi over 5 cubed over 3 factorial plus pi over 5 to the fourth over 4 factorial. not 4 factorial, sorry, 5, minus pi over 5 over 7 factorial plus, pi over 5 to the 9th over 9 factorial. Let me see. So that's 1, 2, 3, 4, 5. And that's going to get you approximately about 0.588.